So let's just specifically look at part D. Is that all right? And then we can look at that in context of A, B, and C as well. So we're given a position, and we want to find the average velocity on the interval 1 to 1 plus h. So this is our time interval with this given position function. Recall that the average velocity was given by the slope between those 2 points. So we're just looking at the change in the position. So we're evaluating s of 1 plus h minus s of 1, and then all over 1 plus h minus 1. Okay, so let's maybe drop down here and compute some of these things. So do you have your calculator handy? What's s evaluated at 1? Negative 763. 56. And yeah, I guess that's all we need here. So then computing s of 1 plus h, it's a little more abstract because we're going to get an expression involving h. So we have negative 7 times 1 plus h squared plus 63 times 1 plus h. Just simplify this as much as we can. We have negative 7h squared. I have 2 h's times negative 7 minus 14h minus 7 plus 63 plus 63h. Everybody okay with that? Okay, let's collect like terms, minus 7h squared. We've got, sorry, that's 60, I said 63h here, right? So we've got a minus 14h and a, where we go, plus 63h. We have 49 plus 49h, and these two terms give us a plus 56. So there's our s of 1 plus h.
Do we not divide by the 1 plus h minus?
Yeah, we do. So we're going to take our two computations here. Both of those go back in the numerator. So let's see, 7h squared, 4956. So we've got our minus 7h squared minus 49h plus 56 minus s of 1. We got what? 56. And then all of this is over h. Do y'all have any questions on that? Okay, so just take note of what's happening here. Part A, B, and C, they're not terribly small intervals. I mean, they are, in a sense, as we progress, we're getting closer to 1. But it's not like the example we did in class where it was like 1.5 and 1.1 and 1.001, right? So, in effect, if we wanted to compute the instantaneous velocity, we would have to compute what kind of limit? The limit as, just looking at what we're doing here, we're computing essentially the limit as t approaches.
Oh, you can finish your statement. I just have a follow-up question.
Okay.
T equals, all right.
Yeah, t approaches 1, right? So, ultimately, if we kept continuing with this pattern, 1 to 7, 1 to 6, 1 to 5, 1 to 4, 1 to 3, 1 to 2, 1 to 1, right? We're getting closer and closer to a fixed value of t equals to 1. That right end point of the interval is what's being altered from 10 to 9 to 8 to some generic thing, 1 plus h. Yeah.
Would it be plus 49h on the right side of you?
Oh yeah, plus 49h, thank you. Yeah, so what did, sorry.
So my question is, in an exam, if we have one of these kind of questions and we have A, B, C, and D, where D is 1 and 1 plus h, could we use the 1 plus h version to solve the other equation?
Of course.
Okay.
So the question was, if we had a question like a table like this on the exam, where we had to compute subsequent intervals or average velocities over smaller and smaller intervals, could we just start off with doing something like this, and then use the result here to compute the rest of the table? And the answer is yeah, you can. It's all really the same thing. I'll erase this, but here if we take the limit as t approaches 1 on all of these average velocities, what that's going to give us is the instantaneous velocity. But notice letting t approach 1 is the same thing as here letting h approach what? Yeah, so if in this thing right here, if we let h approach 0, doesn't that right endpoint approach 1 as h gets smaller and smaller and smaller? Because all h indicates here is a step size. How far away are you from 1? So if I said I want to be half a unit away from 1, then h is a half. If I wanted to be a tenth of a unit, then h is 0.1. Okay. So we could also compute this limit as h approaches 0 on our configuration here. And you might recognize this maybe in a more generic sense. So f of x plus h minus f of x all over h. Does that look familiar? What do we call that?
Difference quotient?
Yeah, the difference quotient. Is it more familiar or less familiar now that we've labeled it? So this is our difference quotient. What did the difference quotient give us?
Average rate of change.
It's the average rate of change. Or the slope of a secant line. You didn't, when you were doing this in pre-calc, you just didn't have that context. So guess what? If I let h go to 0, I'm computing an instantaneous rate of change, not an average rate of change anymore. So it's the same thing we're doing here. This is our difference quotient. This is function at something plus h minus the function at that value. So just replace that x in the difference quotient with 1. Our h is still h. You're looking at the identical statement, except for we're talking about a function of labeled s instead of f. Does that make sense? Any questions or comments about that? Okay. Let me get rid of this stuff here. So in effect, what we're working with the our calculation here is a difference quotient. It's the same thing as the average rate of change. It's the same thing as the slope of the secant line, and so forth. Okay, so what do we have? Negative 7h squared plus 49h all over h. So just maybe in the back of your mind, even though we're not computing a limit right now, we're just simplifying this quotient. Keep in the back of your mind, if we were computing a limit and h was going to 0, initially when we look at this, we have an issue because the denominator is approaching 0. We can't say it's this number divided by 0, right? But what happens here, we see, is that one of the h's in the denominator divides away. And so ultimately, if we were computing a limit at 0, you would be able to compute this limit because it cancels out this h in the bottom here. So we have negative 7h plus 49. And so that function of h says that in relationship to 1, no matter how far away we are from 1, that function of h is always going to give me the average velocity for this particular function in relationship to the t-value of 1. So if we go, let's say, part A, for instance. I don't know why it does that. So if we then revisit part A, where it's having us compute the average velocity on that interval, what's h equal to here?
9.
Does everybody agree? H is 9. Because if this right here is 1 plus h, then h is equal to 9, right? So all we've got to do is throw h equals to 9 into our function we computed. What was it? Negative 7h plus 49. And then we have the average rate of change on this interval without necessarily having to compute the change in y over the change in x. Plus 49.
So ultimately on the homework, you just started with the last problem and just plugged in check.
Yeah.
That hurts a little.
Honestly, and unless you're like really efficient with your calculator, doing that first is probably more efficient because we end up with a simpler thing, just a linear thing involving h. So any of these types of quadratics, we'll see later in chapter 3 why this is the case, but any quadratic position function, when you're simplifying its difference quotient, so to speak, it will always end up being a linear function. So it's going to be a lot easier to evaluate than, let's say, evaluating s of 10, subtracting off s of 1, dividing all of that by 9, right? But whichever you prefer, please do, because it doesn't really matter. Everyone doing this correctly is going to get the same results no matter what route you take. All right. Any questions or comments on that? Do I need to scroll back down? All right. Are there any other questions on the homework?
Is this going to be uploaded to G2L?
Yeah, I'll upload this. It'll be separate than, from our notes, but it'll be there. Everybody have what they need there? I'll go ahead and save that. So, anyone need a 2.2 handout? So we'll begin 2.2, which we start here in 2.2 to get a sense of how we evaluate limits, although it's not the definitive way that we're going to use to evaluate limits. So the first thing here is our preliminary kind of working definition of what a limit is. So we've got a function that's defined for all x values near a, except possibly at a. It's super important in that first sentence. What that's telling us here is that when we evaluate a limit, it doesn't matter if the function's defined at that particular x value. So if f of x or the y values are arbitrarily close to L, and we can make it as close as we like, as we'll see in 2.7, for a sufficiently close to x, then we can write this statement here: the limit as x approaches a on f of x equals to L. So if that's true, then we just say the limit of f of x as x approaches a is L. L is some real number. So what we're associating two different things here. We're saying that as x gets closer and closer to some value, what are the y values getting closer and closer to? So those two things are associated, whereas these two things are associated. So as x does this, what does y do? The limit, capital L, if it exists, just depends on the values of the function near a, not the value at a. So for example, if we look at this figure here, we can see, kind of hopefully make a little bit more sense out of that definition and what it means to actually look at a limit. So let's compute, given this figure, let's find a few things. One, let's evaluate f of 1. So what's f evaluated at 1? Yeah, f of 1 is equal to 2. Now let's look at the limit as x approaches 1 on our function is f of x. So the way we're reading that limit statement is, as we get closer and closer to an x value of 1, what are the y values getting closer and closer to? Notice we're not saying when x equals 1, what does y equal to? The limit is a different statement altogether. As we get closer to 1, what does y get closer to? 2. Yeah, it gets closer to 2. So we're thinking about, when you're given a function like this is like your road. It's the only road you can travel on. So if I'm going to get closer and closer to this x value here, I have to travel along this road. See, as x gets closer and closer to 1, y gets closer and closer to 2. We see that what we've mentioned above, right above the label for figure 2.7, it does not depend on the value of f of a. Sometimes it does work out to be that way. Here's a prime example. F of 1 is 2, and the limit as we approach 1 is also 2. That's more of a general statement above. It does not depend on the value of f of a. It's just a general statement about any function. For some functions it's true, for some functions it's not. Okay. How about, let's compute f of 2. f of 2 will give us what?
5.
F of 2 is equal to 5. How about the limit as x approaches 2 on f of x? 3? What do y'all think? 3? So we might pause and say, well, the function, the piece that I'm traveling along anyways has a hole right there at that y value, because the function's not defined at that particular location. But remember, the limit is concerned with, as we get closer and closer to 2, what do the function values or the y values get closer and closer to? So as you get closer and closer this way or this way, the y values do indeed get closer and closer to 3. Even though there's nothing really there, right? You can imagine these values right here as like 2.9, 2.999, 2.99999, et cetera, and the ones right directly above it, 3.01, 3.00001, et cetera, et cetera. So is everyone okay with this? Are there any questions on that? So it's a big change in the way we've thought about, working with functions before. Because we're really not evaluating a function at that particular a value. We're just looking at what do the y values approach as x approaches 2 or 1 or whatever. Yeah.
Can you just repeat one more time how we're supposed to verbally say that? Like it's the limit of f of x as x approaches 2, is that it?
Yeah, the limit as x approaches 2 on f of x is equal to 2. Meaning that as x gets closer and closer to 2, the y values get closer and closer to 3. Any other questions? Okay, how about f of 3?
Doesn't exist.
Okay, right. F of 3 doesn't exist. We have that hole there. So what's the limit as x approaches 3? What do y'all think? 4? Yeah, so as x gets closer and closer to this value of 3, the y values get closer and closer to 4. So again, these last two examples are showing that the function value, f of 3, f of 2, are not always the same as the limit. It really just depends on the function itself. But it's showing us that to evaluate a limit, it's not as straightforward as just taking the number 3, 2, or 1 and just plugging that into the function. Any questions on this? Yeah.
So on the homework, if it doesn't exist, we just put the anywhere.
Yeah, typically it doesn't exist. If they want something different, then they'll specify. Any other questions? We do have more examples like this later in the section. All right. So is everyone okay with the idea, at least the basic idea of a limit at this point? All right. One-sided limits. So the prior page here, this definition here, notice it was just the limit as x approaches a. When we talk about one-sided limits, now we have the superscript attached to the a. Okay. So a right-sided limit or a right-handed limit, we're approaching x, or sorry, x is approaching a from the right-hand side. It's really the only modification in the definition that we used. So as x approaches a from the right, that just means x is larger than a. So all values larger than a we're approaching through. Similarly here for the left-sided limit, we've got the superscript of the minus. I don't know if that does show up on your printout. Okay, so it's like that. X approaches a from the right on whatever function you have, and the limit as x approaches a from the left on this function. And if we're approaching it from the left, simply means that x is smaller than a. The idea is still the same, however, as we get closer and closer to a from the left or from the right, what do the y values get closer and closer to? That idea is still the same. Why would we need a one-sided limit?
The graph jumps.
Okay, if the graph jumps, so like if your graph looked like this, for instance, remember we're thinking about the pieces or the function itself as the road we're traveling along. So this piece right here, it only makes sense to approach a from the left-hand side. There's nothing to the right of a on that piece. Similarly, the top piece, it makes sense to only approach a from the right. Any other scenarios? We might need a one-sided limit.
Asymptotes?
Yeah, what kind of asymptote?
Slant. I don't know what I'm thinking of.
Yeah, so, if you had like a slant asymptote, I guess, that could be, like what if we had a slant asymptote like this? I guess sort of depend on the configuration, but typically though, I guess those things would be partitioned pretty well. If we're trying to approach something outside here, it doesn't make sense to use a one-sided or a two-sided limit there. So maybe not so much with the slant asymptote, very similar to a horizontal asymptote, but vertical asymptote, certainly it makes sense to approach from one direction. Right, because our vertical asymptotes are kind of cutting the xy plane into different pieces. So I don't know, let's say our function was doing this. Specifically, if we're approaching the asymptote, right? If this is a, then it would only make sense to approach that on the right-hand side over here and from the left-hand side over here. So a lot of 2.4 is we're dealing with limits as we approach vertical asymptotes. Any limit in the sense of a vertical asymptote, what would that limit be? Like if I approached a from the left, if I approached a from the right, what would those limits be? Infinite, right? Because as we get closer and closer to the vertical asymptote, the y values are getting larger and larger in a certain direction. In that sense, if we said, let's say, the limit as x approaches a from the right on this function is negative infinity, does that mean we have a limit? So either definition you look at, it's the f of x as x approaches a is equal to L, and L is just representing some real number. Is infinity or negative infinity a real number? No, infinity is just an idea, right? Infinity is just a way for us to say that this thing continues on forever in that direction. So these types of limits, although we can pin it down and say the function gets larger and larger in some direction, it's not a finite number, so in that sense, there's really no limit here with those types of things. So just because we can represent it as an abstract concept doesn't mean the limit exists. Okay. So two common scenarios why you would need a one-sided limit. Do y'all have any questions on any of this? So notice when we looked at that first example and when we're computing these limits, 2, 4, and 6, that those were two-sided limits because we don't have this subscript or superscript here attached to the numbers. So in our minds, we're just approaching that graphically from both sides simultaneously is what's happening. And so maybe thinking about that graph previous to this page, the relationship between a one-sided and two-sided limit is given to us in this theorem. And basically what it's telling us is that if my two-sided limit exists, and it's equal to L, some real number L, then what that implies automatically is that both my right-handed limit and the left-handed limit are identical to that number L as well. So let's state that for the two-sided limit to exist, both the right and left sided limits must be equal. And we'll just keep it consistent with text notation. Maybe we'll say for it exist and equal L. So basically, if we're analyzing the two-sided limits and we see that the one-sided limits rather, we see the one-sided limits are identical, then that automatically implies that the two-sided limit has to be that number. Moreover, if the one-sided limits exist and equal L, the two-sided limit must also equal L. So that's the nature of if and only if statements. Or the if and only if statements are like, you can read them both ways. Whether you change the argument or not doesn't make a difference. So like the if and only if is like a two-way street. I can read it this way and I can read it that way. There's a lot of theorems and stuff you see in math that'll say, if this happens, then this happens. Those statements are only meant to be read one way. You have to have this thing occurring before you can conclude this thing. But if and only ifs, you can look at it either way. If these two things happen, then this is true. If this is true, then these two things happen. So not only do we get sort of the positive implication of the if and only if statement there, but we can also look at the negative implication of what that theorem is telling us. So really, it's not meant to be confusing or overwhelming, but really you've got four statements out of that one single statement. Okay. So if the two-sided limits, sorry, if the one-sided limits from the right and from the left are not the same, what do you suppose that means?
The two-sided limit doesn't exist.
Right. So we just said earlier, in order for that two-sided limit to exist, that both of these things have to be equal. Well, if both of these things are not equal, then the two-sided limit does not exist. And finally, what we can say as well is if the two-sided limit doesn't exist, then what do we know about the one-sided limits? Yeah, they're not equal. So yeah, they should look like similar statements because they are. Again, that's the nature of the if and only if statement. If that were a conditional statement, if then, you wouldn't get so many different ways to look at it. So a prime example, as we mentioned, are piecewise functions. When you're computing limits on piecewise functions, as we'll see, it's super inefficient to graph every function you want to look at a limit on, right? Like if you had a piecewise function with 5 different components, before you computed 1 or 2 different limits, you wouldn't graph that entire thing. It's not efficient to do that. So in that sense, it's, you know, these things can help us determine a two-sided limit on a piecewise function. Okay, so like for instance, the example we drew here, oops. Say we didn't have that graph, we just had the function's definition and we wanted to compute the limit here at this x value, a. Well, we compute from the left and from the right and see that they're not the same y value, right? Maybe this is, I don't know, maybe this is a y value of 1 and this is a y value of 2. Then by implication we get that the two-sided limit doesn't exist. So these things that we mentioned here from this theorem are utilized a lot with piecewise functions especially. Do y'all have any questions or comments on this? Okay, so we'll take a look at this example here. So let's find the limit as x approaches 2 from the left on this function, which is g. So what do y'all think? 4? 4. Who agrees with 4? So remember again, as we did the first example or the first graph, we've got to follow the path, we've got to follow the function, but this time we're saying that here's x equals to 2. We've got to approach that from values smaller than 2 or from the left. So the only path we have to travel is this one. And as we get closer and closer to that x value of 2, the y values get closer and closer to 4. So how about the limit as we approach, as x approaches 2 from the right? What would that equal? 2?
Oh wait, 1, sorry.
Okay, 1. Again, here we're approaching this x value of 2 from the right-hand side of 2. We can only travel along this path. Those y values are getting closer and closer to 1. Are y'all okay with that? Makes sense? Okay, so what's the limit as x approaches 2? Right. The limit as x approaches 2 on this function doesn't exist. Why?
Because the one-sided terms don't.
Right, yep, exactly. The one-sided limits are not the same, therefore that limit doesn't exist. Questions on that?
So are those like the only two cases where limits don't exist? Like if the x value approaches infinity and if it's a piecewise?
Yeah, so the only instance where a limit doesn't exist, we've seen one here where the one-sided limits are not the same, meaning that you've got a jump in the graph. Because we saw earlier with the first example, even though the function is not defined, this function is not defined at 3, we were still able to define a limit as x approaches 3. Okay. The difference here with that last example is the nature of the jump, or the gap in between here. So yeah, that doesn't exist, and when we approach infinity, it doesn't exist. There's, well, yeah. Any other questions? Honestly, we don't do a whole lot with limits and graphs. So this is sort of just to get us into the idea of what a limit is. Primarily when we're dealing with limits, like I said last time, it's all done by hand. We don't want to have to graph things every time. And even if you graph stuff, like if I look at a graph on the computer, as we'll see when we go through some more exercises later, it's not always accurate. You've got to know, like, analytically what's happening on this graph. Has anybody ever used Desmos? Have y'all used that before? Yeah, so there's a phone app for this if you want to use it. A lot of things on your homework will have you graph stuff anyways. But the idea is, if you've used this enough, you've encountered functions that might have a hole in them, but the holes don't show up on the graphs, right? Like your calculator or your software isn't going to show you explicitly that there's a hole somewhere. So that's another danger in using, just a graphical approach to ask questions about limits. So I've got a few more examples looking at limits, so we can kind of get the idea. Hopefully y'all can read that. Can you see it on the board at all? I don't know if it's any better. I couldn't make this part any bigger, so I apologize. Okay, so this function g, what's g of 0? 0. What's the limit as x approaches 0 on g of x? 1. So again, take note, that's a two-sided limit. As we approach an x value of 0, the y values get closer and closer to this value, which is 1. G of 1 equals 2. And the limit as x approaches 1 equals 2 as well. Again, another two-sided limit. So we're approaching this y value here. Make sense? Questions on that? Yeah.
Is that point at 0, 0? Is that a point? Is that
Yeah.
a point? Okay.
Yeah.
So how do you know, like, if there's like a point way off somewhere? Like, how do you know they're not talking about that? Do you just look on just wherever there's like an actual line on the graph?
Yeah. So like, if you mean like a point way off, like if it were like down here and didn't show, like.
Like if there was a point on the graph at like -2, 1.
Like here.
Yeah. Like, how do you know? Do you just not really count that?
So if I mean that's part of the function.
Okay.
If we just had that point there at -2, 1 as well as the parabola with the hole and this point here, there's really nothing we can do to approach this, right? You can't approach a point from the left or from the right. So like the function would exist here at -2. We can define our function at -2 as 1, but in this sense we couldn't define a limit because there's no path leading up to it,
Right.
either from the left or from the right or from both sides.
Okay, that makes sense.
Yeah, thank you for the question. Any other questions? Okay. Oh, this one's even worse. So part A is, if you can't see that, part A is f of 2. So what's f of 2 equal to? F of 2 equals to this point right here, just 2. Part B is the limit as x approaches 2 on f of x. So what was it? You'll think 4? As as x approaches 2, the y values approach 4. Yeah, no, maybe? Okay. Is it tough? The limit as x approaches 4. On f of x. Also equal to 4. Do y'all agree? And the limit as x approaches 5. Yeah, here's 5 right here. We're approaching this value. Questions on that? It's worth pointing out that we've seen a couple of occurrences of where the limit does equal the function value, and we've seen occurrences where the limit doesn't equal the function value. So again, evaluating a limit in general on a function isn't as straightforward as just plugging that into that value into the function. And in 2.6, so a little bit down the road, we look at when we can actually plug that value directly in and when we can't. All right, so we've got g of x here. There's quite a few of these involved in this graph here, but let's evaluate g at 2. It's g evaluated at 2.
3.
G evaluated at 2 equals to 3. We'll fit this here. Okay. How about the limit as x approaches 2 from the left on g of x? 2. As we approach this x value from the left, we're only allowed to use this piece right here. So the y values get closer and closer to 2. Okay, how about as x approaches 2 from the right?
3.
As x approaches 2 from the right, we have to use this piece right here. So the limit there is 3. So what do we know about the limit as x approaches 2? Doesn't exist. Clearly we can see that on the graph because we've got the jump, but again, if ignoring the graph, we've got the left and the right limits, but not the same, so we automatically know that that limit as x approaches 2 does not exist. How about g evaluated at 3? G evaluated at 3 is equal to 2. Okay, as x approaches 3 from the left, what's the limit? Sorry? 3? Y'all think 3? Okay. Approaching 3 from the left, using that piece. The limit as x approaches 3 from the right? 2. Okay, good. 2. We have to use this piece. So it doesn't ask us, about the two-sided limit at 3, but f and g, parts f and g tell us that that limit doesn't exist either. Algebraically, visually, we see again there's a jump there. So it's all coinciding. G of 4?
4 for 3.
Yeah, g of 4 is equal to 3. And the limit as x approaches 4 is also 3. Because we're able to approach that from both sides simultaneously. So, this kind of gives us some insight on a piecewise function. If I gave you just some piecewise function defined however it is, let's say it's 2x for x smaller than or equal to 1, and 5x minus 1 for x larger than 1. Part H and Part I kind of tell us that we didn't have any issues here with evaluating the limit at 4, for instance, because 4 was completely contained within one piece, right? Totally contained within this. So is 4.5, so is 3.5. It's only on these piecewise functions where we start approaching these endpoints of the various pieces where we have to start looking at two-sided limits, right? So again, think about this piecewise function defined algebraically. We don't have this visual information, but we know that this piece, this linear piece here, is only defined for values that are smaller than 2. And then the next piece is defined for values that are larger than 2, right? So once we see a limit at 2, we have to pause and say, all right, I need to look at a one-sided limit because I have this piece stopping at 2 and this piece starting at 2. And really, when we're doing that by hand, what we're checking for is, like our work here in part E, F, G, and H. What we're looking for is, do these pieces actually exist as individual components through the one-sided limits, or did I compute this limit as some sort of a y value, right? And then I look at the next piece and I compute the same y value as this limit. So are those pieces actually disjoint, or are those separate pieces connected? The y values that emerge from our limits would tell us that, right? This would have a different y value. Maybe this is a y value of 1, and this is a y value of 2. We know, since that those limits don't exist, that the one-sided limit, approaching it from both directions, doesn't exist. But graphically, what that's telling us is that those pieces don't meet up. If I compute the limit on this piece and it says that that y value is 1, and then I compute the limit on this piece and it says the y value is 1, then graphically I know those pieces meet up. Does that make sense? Okay, because that's where we're moving towards. We're not going to be looking at graphs to answer questions about limits. Any questions on any of this? Comments? Yeah.
So if you don't have the graph, for example, with the piecewise zero, how would you find them just for each part, and then have all the different limits?
Right, and then you're comparing numerical values at that point. So how we actually evaluate limits on this, we'll see in 2.3. But remember, moving forward, if I ask you for this piecewise function, for instance, to compute the limit as x approaches 0, then we can just plug that directly in, because 0 is totally contained within this interval. If I say compute the limit as x approaches 1,000, then I'll just plug 1,000 into this, because 1,000 is totally contained within this interval. But in any other value, for that matter, is x approaches 1.1, then you can plug it into that function there because it's completely contained. The only reason to pause and say, hey, I need a two-sided limit here, is if I ask you to approach 1. What's the limit as x approaches 1 on this function? you've got to look at it from the left and from the right. That would be true for any number. I can make this any number. I can make this 7. If you compute the limit at any number other than 7, you just put it in its corresponding piece. But the moment you have to compute the limit at as x approaches 7, that's when you're going to look at a two-sided limit. Or sorry, a one-sided limit from both pieces. And then at that point, what you're looking for is the limit here, the y value, the same as the limit here? Because if it is, that means you have this scenario. Those pieces are joined up. If those two limits are different as we approach 7 from the left and from the right, then you have a scenario like this. Yeah. Okay. Any other questions? All right. So I do have one more thing to mention in 2.2. And really, we'll start off with the question, why can't we use graphs or table of values? We'll say or a table of values. So how come we can't use graphs or table of values to compute limits? A table of values, again, is something we did in 2.1 for computing those average velocities over smaller and smaller intervals. That was where we were looking at a limit there. 2.2, it was mainly graphical analysis. So we're going to use we're going to look at a really drastic function to kind of illustrate our point. But if there's one example like that, then there's thousands of examples like it. So let's consider the function f of x equals to the cosine of 1 over x. What's the limit as x approaches 0? 0 on this function.
That's an oscillating function, so it can't have, or it doesn't have a limit, because that's infinity, a cosine of infinity, so you can't have a limit.
Okay, that's a good rationale. So the rationale was this is an oscillating function. So how could we have a limit on a function that oscillates? Well, this is probably beside the point, but just to kind of clarify, if this was our oscillating function here, and I said find the limit, maybe this is pi, I said find the limit on this function at pi, could we do that? Yeah, totally. It's whatever this y value is. There's our limit. But maybe then what we're noticing is that x is approaching 0. What happens to the argument 1 over x as we look at smaller and smaller denominators?
It approaches 0.
It's what?
It's going to approach 0.
No, well, right, the denominator is approaching 0, but what happens to the fraction?
It approaches infinity.
It gets larger and larger, right? So 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000. It's getting smaller and smaller and smaller. Or sorry, larger and larger and larger as the denominator gets smaller and smaller and smaller. So then we might say, well, now we're looking at cosine of something that's infinite. How can we conclude, if this thing keeps on keeping on? How can we say that way out here at infinity it does have a limit, right? That doesn't make sense, does it? Or does it? Do limits out at infinity work? No. Maybe not in this example, right? Maybe not in the sense of an oscillating function. Can you think of an instance where we could compute a limit way out at infinity?
If there's like a horizontal asymptote.
Yeah, exactly. If there's a horizontal asymptote, like if my graph did all this stuff and then it flattens out, as I go further and further out this direction, aren't I approaching the horizontal asymptote? Yeah. But intuitively, this is probably not the case with cosine, right? Because we know it does this. It's not an easy function to graph either. So we might say, all right, well, let's just start off with a table of values. By the way, your calculator should be in radian modes, not degrees. So let's just start off with a table of values. And let's look at, so we'll have x and cosine of 1 over x. Let's plug in 3 different values close to 0. Remember, x is approaching 0, so let's do 0.001, 0.0001, and 0.00001. Cosine of 1 over 0.001. Somebody get that?
.5623.
Okay. .5623. Anybody have the next one?
Negative 0.9522.
Negative 0.9522. And cosine of 1 over 0.00001. Negative 0.9993. Okay. So we might say, well, I did a good job. I got pretty close to 0, didn't I? Does it look like there's a definite pattern in cosine of 1 over those numbers? Perhaps, maybe this was like a fluke, right? We had a positive half, then now it's negative 0.95, then it's negative 0.99. So, you know, we might be led to believe that if I looked at another value, that this would be approaching what? Negative 1. We might think that's approaching negative 1. So does this actually approach negative 1? So I'm just going to cheat and put the rest of the values from your textbook in here. Here. So let's just say we stopped there because we were tired and we didn't want to do it anymore. We can see, though, if we were to keep going, that after our negative 0.99936, that even closer to 0, then it jumps up to positive 0.9, then it's back down to negative 0.9, then it's back down to negative 0.3. So the table of values, if we keep going, we do see those jumps, right? It's not honing in on a particular number. It's not like 0.00003, you know, or something to that effect. Oscillating between positive and negative values. So table of values there, it's not good. It doesn't give us any information. again, this is a dramatic function just to illustrate our point, but there's more out there like it. Okay, so then how about the graph? So it's fine outside of 0, right? But when we get closer and closer to 0, it starts to look weird. In fact, it doesn't matter how far we zoom in, it's still going to look like trash. We can't see a particular value. So let's see, I think your text has that too. What's happening is we can see here it's a different scale, but what's happening is that the oscillations start to become so rapid that it starts to look solid. Even though you have these oscillations in there, if we could zoom in, we would see these oscillations, but it's so rapid towards the origin that we can't see it. It just looks like a solid line. And of course, that's, the text was illustrating 0, approaching 0 from the right-hand side, but from the left-hand side it's symmetric, so it's doing the same thing. Okay, so there's our dramatic example. Graph's not helpful, table of values isn't helpful, so then we need to come up with more robust, like analytical methods to evaluate limits. So we'll just end this by saying, in order to compute this limit, we have to see section 2.3, which is where we'll pick up after break. Do y'all have any questions on any of the things we've done there? All right, let's take a 10-minute break and then we'll start 2.3. If you haven't printed out 2.3, you might want to do that, if you want to. So in 2.3, we'll look at techniques for computing limits. And really, we're just looking at an array of functions in this section. Linear functions, polynomials, rational functions, and then we'll just say other. So if you look at theorem 2.2, we're starting off with the linear, kind of like you did in pre-calc, linear, then we look at polynomials, then we look at rationals, and then other. But theorem 2.2 says that a, b, and m are real numbers, and for a linear function, mx plus b, the limit as x approaches a is any value, is determined by plugging a directly into the function. Okay. So whatever x is approaching, we're just plugging that in to the function itself for x. Now, I guess if we looked at just a graph of some linear function, so we could just see visually that hopefully it totally makes sense. So there's our f of x. Regardless of where I'm at, let's say here, that's our a. Regardless of where I'm at on the line, everything in essence, in terms of a limit, is completely contained within that line. So my y values, as I approach from either side, or just whatever the function value is for that particular x value. So really what this theorem is saying that in words for us is that to evaluate a limit on any linear function, we can directly substitute the direct substitution does evaluate those limits for us. All right. For instance, if we had to evaluate the limit as x approaches 0 on negative 5x minus 6, I will say that the more efficient you are at recognizing particular types of functions, the easier it's going to be when it comes to evaluating limits, because you already know a great deal of information about many functions. So when we compute a limit on a particular function, if I recognize that as, you know, a linear, a polynomial, a rational function, then I already have a sense, an algebraic sense as what to do with that function if something needs to be done. But all this equates to is just plugging in what we're approaching for x. So we evaluate that by direct substitution. Do also keep in mind, for instance, let's say as x approaches 0 on the function 32, what would that limit be? 32, right? So 32 is just a constant function here at 32, right? Doesn't matter what x value you're approaching, the y value is always 32. As a more general sense, if we're computing the limit as x approaches anything, and you don't see an x involved in that expression, then that thing is a constant in terms of x. So there tends to be confusion, especially when we start looking at, you know, all of our derivative rules in chapter 3, even a lot of limits too, recognizing things as constants when they need to be recognized as constants. So like the limit as x approaches 2 on function e is just e. Or pi would be just pi, etc. Especially when we start looking at derivatives. Derivatives of constants versus derivatives of other types of functions really start to trip people up, at least initially, because, you know, there's thousands of functions that we have to look at and say, well, what kind of function is this? Because I need to know what kind of function this is before I apply a certain derivative rule. If it's a product of two functions and I'm applying a quotient rule to it, you're not going to get the right answer. So recognizing a function, whether it's a constant, a composition, or a rational function, etc., it becomes really crucial, especially when we're dealing with derivatives in chapter 3. So that's about all we're going to say for linear functions. Do y'all have any questions, or does this seem pretty straightforward? So for whatever reason, this page ended up blank, so I'm just going to delete that. Perhaps we're missing a rule. Let me go back rather. I don't know why it's. Let's see. All right. So this was actually missing from your notes. I do apologize for that. I had issues converting some of these notes. And honestly, I didn't have a lot of time to verify every page. So we're not going to really justify these. We're just going to take them as they are. Again, these will be on the notes that I post to D2L. So I wouldn't honestly worry about copying them down. We don't have to have these things memorized. I don't really test you over theorems. A lot of things, if something does show up on the exam related to a theorem, it's really something that you should know. I don't expect a verbatim regurgitation or memorization of these things, but just have a working knowledge of what it's saying is all I ask. And these laws tell us, in certain instances, what can we do with that operation of a limit. Okay, so for instance, if I have the sum of two functions that I'm taking the limit of, that limit operation can get distributed. And so instead of looking at the limit of a sum, I can take the sum of each limit. Does that make sense? Same thing with the difference. The limit basically is distributing across and applying to things that are separated by addition and subtraction. So, for example, 1 and 2, if we had to compute the limit as x approaches 3 on, I don't know, let's say x to the 4th plus x to the 5th, then I can just look at the limit on each one of those functions and add that together. So the limit as x approaches 3, excuse me, on x to the 4th plus the limit as x approaches 3 on x to the 5th. And again, it doesn't matter if that was plus or minus, it works the same way. So in effect, we can distribute, we use that term loosely, distribute limits across sums and differences. And you'll notice that all of the other rules are fairly similar to that. A constant multiple, so if I have just some number times a function of x, very closely related to the limits we looked at on a constant, that constant doesn't involve an x. This limit only operates on something that involves x. So that constant can get pulled out. We can compute the limit and then multiply by that constant after we find the limit. So if that's 3. For instance, the limit as x approaches 0 on 3x squared, we can say that's 3 times the limit as x approaches 0 of just x squared. So there's our function of x, there's our constant that got pulled out of the limit. Is everybody okay with that? Does that make sense? So we can pull constants out, distribute across sums and differences. 4 deals with the product. So if I have the product of two functions, Again, the limit can be distributed to both factors or all factors and computed individually. So we have the limit as x approaches, let's say x approaches pi on sine x, cosine x. Then I can look at the limit as x approaches pi sine x times the limit as x approaches pi cosine x. And honestly, when you do the homework, at some point, I hope it's you're very efficient at really just kind of doing these things without writing down each individual rule that you're using. Because otherwise, evaluating limits would be tedious if we broke it down in the sense of all of these rules individually. And so we can start putting rules together. If I've got the product of two functions plus the product of two other functions, then I can break those up using 1 and 2 and number 4. So the limits distribute across a product. Same thing with the quotient. The limit gets distributed, if you will, to the numerator and the denominator. And then here, as always, our stipulation is provided the denominator is not 0. So just so we're not dividing through by 0. So the limit as x approaches 5 on like x squared. Let's just do x squared minus 1 over x plus 1. Says that we can view that as taking the limit as x approaches 5 of our numerator and dividing that by the limit on our denominator. So if then at this point we see that other rules apply, especially the sum and difference, we could also write that out in that way. Yeah, it's not terribly efficient to do this, but just to illustrate what we're able to do with limits. But really we could view the top, the numerator is the limit on x squared minus the limit on 1. Distributing across the difference there. And then the bottom. Across the sum. And really it's just like if we look at these rules individually on a lot of different types of functions like this, what we're working towards is breaking each individual limit down so that it's the limit of a linear function, and then we can default back to that previous theorem. It says, oh wait, this is the limit on a linear function, so I can just plug 5 directly in for that x on the bottom. This is the limit on a linear function 1, so I can just plug 5 directly in there, still 1. So that's kind of how your textbook develops. How do we take limits on polynomials, and how do we take limits on rational functions as well? Again, it's a long-winded way to get there, but I don't know. Maybe think about like if you were the one that kind of discovered calculus, and you were trying to come up with all of these justifications on how things work. Like, you would have to go through all of this stuff and prove it mathematically to show that this isn't actually a legitimate thing that I can do, right? So, if it seems overwhelming and tedious, hopefully at least we can appreciate and be thankful that someone did all of this work for us, and then we just have to understand what we're doing. So quotients, products, sums, differences, constants. 6 deals with powers. So if we have a function that's raised to a power, we can move the limit inside with the function and then apply the power afterwards. So for instance, the limit as x approaches 1 on, let's say, x to the 5th. We can write that as the limit as x approaches 1 on the function x, and then we can raise all of that to the 5th power. Or let's say x approaches -2 on the function x minus 4 raised to the 10th. Same thing there. We can say it's the limit as x approaches -2 on the linear function x minus 4. Find that number and then raise that number to the 10th power. And on we could go with that. But just, I guess maybe we're kind of thinking of the power as just operating on that function of x. When we take the limit on some function of x, all we're getting is some number in return. So the limit isn't really affected by this power. What's affected by the limit is wherever we have x's. Anything else in the function does need to be taken into consideration, but it's not directly related to, x being -2, for instance. The statement about the roots is still in line with what we know about even roots versus odd roots. Okay, so we can view roots as 1 over n power. So we can kind of default back to the power rule where the limit can be passed through to the function and then we can apply the power, which in this case is a root, after we find the limit. The only thing we have to worry about is when we're dealing with even roots and those even roots evaluating to negative numbers. So provided that the function is greater than 0, if n is even. So if n is even, then we have 1 over 2, that's the square root, 1 over 4 is the 4th root, right? So that's really the only thing, just like division by 0, we have to worry about. So like the limit as x approaches 4 on the square root of x. We could write as the square root of the limit as x approaches 4 on x. If we contrast that to, let's say, the limit as x approaches -4 on the square root of x, and maybe we accidentally did this. Then we can say, well, underneath the radical, if I just look at the limit itself, that's just the limit on a linear function, right? X is a linear function. So I would say, well, if that's a linear function, I can just plug that -4 directly into that function. But then what that's giving me is the square root of -4, which isn't a real number. So all of that stuff we've learned prior to still makes sense. Now, this one here tells us that we're evaluating the square root of 4, which is 2. So the operation with the limit is a bit different. Hopefully not terribly confusing or overwhelming, even though it's a lot of information there. The same rules of algebra still apply for us. Again, that's whittling all of these types of functions down to where we're just dealing with the limit of a linear function. Like this one, x minus 4 to the 10th, we know that's a polynomial, but we know that if I pass this in, now I'm calculating the limit on a linear function. So I just plug -2 in right here, and then I'll raise it to the 10th power after I've computed the limit. Do y'all have any questions on that? Okay. So then when we evaluate a polynomial, for instance, we see there's a combination of multiple rules there. We've got functions of x separated by addition and subtraction, functions of x separated by a constant multiple of 2, and by a power of 2. So let's just write this out the long way once, and then we'll see what we're actually doing, if you can't see it already. So the limit as x approaches 1, we're going to distribute across the sum and difference. So for those last two terms, they're linear functions, so we can evaluate those limits according to the previous theorem. The first term still needs a little bit of work. We've got a constant multiple and a power. So the constant multiple, it's pulled out of the limit on x, and then we square that. What's the limit as x approaches 1 on x? 1. And the limit as x approaches 1 on 2? So we can evaluate those two because they're linear. Once we apply a couple of other rules, this first term is now a limit on a linear function. So what would this limit here evaluate to? Yeah, the limit evaluates to 1. 1 squared is 1, and we multiply it by 2. Okay, so that limit is equal to 1. Function. So the limit laws are showing us what? In order to evaluate this limit, all we had to do was do what? Yeah, all we had to do was x approaches 1. All we had to do was plug 1 in for x from the very inception. So again, super long-winded way to get there, but technically if we're going through this, we have to build upon the linear stuff before we actually come to that realization and say, well, hey, I wonder if on every single polynomial, evaluating a limit is as simple as just plugging that x value in. What do you think? Yeah, totally is. Any polynomial can be also evaluated through direct substitution in combination of those two theorems that we've just looked at. So let's state that as well. Any polynomial let's specify that we're talking about a limit. So any limit on a polynomial function be evaluated by direct substitution. So let's look at, notice we said any limit. Doesn't matter if it's a two-sided or a one-sided limit for any polynomial. So if I ask you to compute, for instance, the limit as x approaches 1 from the left on x to the 4th minus 3x cubed plus x squared minus 4. That's where the recognition of functions comes in handy. I recognize that as a polynomial. So I'm just going to plug 1 directly into that for x to evaluate that limit. And take that, plug it in here. We have plus minus 2 plus 1 minus 1 minus 5. So that's how we would evaluate that limit. You don't really need to go through all of those rules to do that. It's easy, right? Simple. There's a lot of justification to get to that point. Do y'all have any questions or comments on this?
That's only on polynomials, right?
Polynomials and linear functions, yeah. So linear functions rather are essentially polynomials. They're just a first degree polynomial. Yep. Okay, I guess I had that already, but anyhow, even one-sided limits, we just plug that value in. If you think about a polynomial, they do this, right? So polynomial. Doesn't matter where you're at or what you're approaching. If I approach that from the left or from the right, it makes no difference. Any other questions on this? All right then, so what happens when we look at the ratio of two polynomials? We know that the limit laws say that if I'm computing the limit on a quotient, I can look at the limit of the numerator, divide that by the limit of the denominator. The stipulation there was that I can do that as long as the denominator doesn't evaluate to 0. If the denominator does evaluate to 0, then we've got issues. You've got to do something in addition to just plugging it in. So the example 1, what would the limit be there? Just take a minute to compute that. Okay. 1/5? What do you think? The only issue here that we're looking for, again, is division by 0. If x is 1, and I plug that in there, my denominator is 5. So this thing is totally fine to proceed with. So I'm going to take x equals to 1 and plug that in. In these examples that we've looked at, and with any limit, really, it's also important to understand what that statement is telling you about that particular function. A lot of times you'll just see evaluate this limit, and then you move on, evaluate another one, and you keep going. Particularly if we looked at the function 2x squared plus x minus 2 over x plus 4, what do we know about that function? Does that limit tell us any information about that particular function?
Or negative.
Do what?
X cannot equal -4.
Okay, yeah, so just from an algebraic standpoint, if we looked at that function, we know x can't be -4, right? So that's the only restriction of the domain, is x not being -4. So what happens on this graph as we approach 1? The y values approach 1/5. What is that on the graph? Is it something weird, or is it just there? Okay, so yeah, that's what I'm getting at. Is this telling us that we have a hole there, or is that an actual solid point on that graph?
It's a solid.
Yeah, how do we know it's a solid point? Yeah, because the 4 is where it's undefined. The function's not undefined at 1, so, whatever this function's doing out here, as I approach an x value of 1, my y value is approaching this number, which is 1/5. That's just showing us we have an actual point in that graph. It's really not anything mystifying, right? But, we knew that, maybe, but now we're putting that into the context of a limit. What does that limit tell us? Well, it pretty much tells us what we already knew. It's not until we start to get to functions like in example number 2, where then we have to think about, well, what is that limit statement telling us? So we'll notice in example number 2 that the function x squared minus 4 over x minus 2, x can't be 2. That value of x is not in this function's domain. But as we saw in 2.2, just because a function is undefined somewhere, that doesn't mean that you can't compute a limit, right? So the issue with looking at it like this, according to that previous theorem, is that we have division by 0. So it's not that those limit laws fail us. It's just a different way to show us what we already knew. If I plug 2 into that function, I divide by 0. So really what we need to do is figure out, is there a way to not divide by 0? Can I algebraically finesse this function so that I'm no longer dividing through by 0? Yeah.
That ends up being a 0 on the bottom because
Right.
of the limit. Does that automatically just tell you there's a hole?
Yeah, yeah. So, but then as we move forward, we got to be careful because we know from an algebraic standpoint that the function's undefined at 2, and from there, then we said, well, is that domain issue, does that correspond to a hole, or does it correspond to an asymptote? How do we know something was a hole versus something was an asymptote?
Is that covered later?
Huh?
Is that covered later?
Well, actually, you've covered it before in pre-calc.
Wouldn't we just factor out the numerator and then it would cancel out the denominator, which would give us the whole, and then our new function would just be x plus 2?
Yeah, exactly. You remember when you had a rational function and you had factors in the numerator and denominator that canceled out or divided away? You said, oh, that's the whole. The thing that's left over is the asymptote. Remember that? So that's exactly what's going to happen here. There's no way to avoid that division by 0 as the function stands. But I know algebraically, I can factor the numerator and I can factor the denominator, or leave the denominator as is. So if we factor the numerator, then we see exactly what happens with that function. The issue of dividing by 0, the x minus 2 in the bottom, that gets canceled away with the x minus 2 up top. And so all we're left with now is computing the limit as x approaches 2 on the function x plus 2, which is 4. But we we see that through that process, if we didn't have the limit attached to that function, now we're back in an algebra or pre-calc class where it says, analyze the rational function. It said, oh hey, this factor cancels, so I've got a hole at that corresponding 0. Do y'all remember that? Might have been a while for some of you, but. So what do we know about this function x squared minus 4 divided by x minus 2? As x approaches 2, y approaches 4, but that's not a point on that graph because your function's not defined at 2. So this is telling us also that there's a hole on this function here. What we're saying is that this function, x squared minus 4 over x minus 2, is algebraically equivalent to x plus 2, except this function looks like a linear function that has a hole in it, whereas if we were to graph just x plus 2 looks like this. This function right here looks like this. It's the only difference between this function and the linear function. But in context, right, this function is that function. So if we were to graph this thing, that's what it would look like. We know that this point right here that's missing is corresponding to an x value of 2 and a y value of 4. So that's whatever. Let's look at it like this. That's 2, and that's 4. As x approaches 2, y approaches 4. Does that make sense? So there's our rational function, but again, it's just looking at the graph, it's misleading. Right? It's not until we, hover over that point directly that it tells us it's undefined. So we know for sure there's an actual hole in that graph. The reasoning applies to any function. So our statement here is a very generic statement. When we're computing limits, if the function you're computing the limit on is undefined at x equals to a, and that's in the context of what you're approaching, a is a finite number, but the limit exists as capital N, another finite number, then whatever function you're talking about will always have a hole at that x value and that y value. That's just another procedure to find a hole. Again, you see that you're really doing the same thing you've already done prior to limits, but it's more justified in the sense of a limit. Because you've always been told just from an algebraic standpoint, like if I have this kind of thing, these things divide away. Why do those things divide away? It's equivalent to 1 over 1. It's the same quantity divided by the same quantity, right? Except when what happens? That's always the same number over the same number, except for at one particular instance.
When x equals -1,
When x is -1, this becomes 0 over 0, right? So in prior classes, they just said, hey, that's always 1, just cancel it out. It made sense at the time, right? But it's not always 1. In fact, this is always equal to 1 if x is not -1. Do y'all agree? Well, fortunately for us, go back to this one, in the sense of a limit, we divide this out. This is always 1 except when x is equal to 2. But this operation of a limit, do we care about what's happening at x equal to 2? No, we just care about what's happening near x equal to 2, right? So that's how we get by that here. It's not that, in the sense of a limit, that this is 0 over 0. It's something very, very close to 0, something very, very close to 0. Whatever it is, it's still the same quantity. So all this stuff holds up because if I'm approaching -1 in the sense of a limit, it doesn't matter. It's not saying that x is equal to -1. It's just saying we're close to it. All right. So again, if we approach a number that's not in the domain of a function, but that still gives us a finite number as a result of the limit, then you're always talking about a whole. Do you have any questions? All right, so a couple more types of functions. This isn't a rational function, but we've seen algebraic techniques to simplify these things as well. We've seen both scenarios where we're able to take the number and plug it into the function directly, and like this example or the previous, where if I take this number and plug it in directly, I have an issue. Either I'm dividing through by 0, or I'm taking the even root of a negative number. If any of that happens, then you've got to revamp the problem. So the problem here again is I'm dividing through by 0 if I just plug 1 in for x. So the procedure when you do that is always, is there an algebraic process I can use to eliminate the factor of x minus 1 in the bottom so I'm no longer dividing by 0? And what that entails is I need a factor of x minus 1 up top so I can get rid of that factor on the bottom. So we'll pick up here next time, but if you remember that when you have, like a root plus or minus something else, we can involve the conjugate to simplify that algebraically. So if you forgot that, maybe look over, and then we'll talk about in a certain instance, like this particular example, it doesn't always work, but in this particular type of examples and others like it, where we can just factor. So we'll look at both methods to evaluate that. Y'all have a good weekend. Be safe.